Design of a basic pumping facility, Raimundo Ferreira Ignacio. Class 2. To really be learned, the class must motivate study daily and lonely. Hydrostatic. Study fluid at rest. Constant level. Pressure. Pressure defined as the modulus of normal force per unit area. Pressure is equal to the ratio between the magnitude of an elementary normal force and the elementary area where it acts. Therefore, the module of the normal force acting on a given surface and which was caused by the pressure is obtained by the integral of pressure times the elemental area, dA. Advantage of fluid over solids. T. The force applied to a solid maintains the original direction that is applied. In this case we can only change this situation through gears that can be subject to breakage. In fluid, the normal component creates pressure that propagates in all directions and where there is no risk of breakage, see figure. It's good to remember that if the pressure is constant, it results that the modulus of the normal force is equal to the pressure times the area where it is applied. This is because, being constant, it went outside the integral, and the integral of an area element, dA, is the area itself. We must always know that pressure is different from force, because the same force can result in different pressures. Reflect on the figures below. In figure A, we have a pressure of 10 Newton per square centimeter, and in figure B, a pressure of 20 Newton per square centimeter. So the same force of 100 Newton gives rise to different pressures, and this proves that force is different from pressure. Don't forget that Pascal is equal to Newton per square meter.
I understood.
At this point, I will recall the concepts of effective pressure scale and pressure in a continuous fluid point at rest.
Effective scale is one that adopts the local atmospheric pressure as zero. Therefore, in this scale there are negative, less than atmospheric pressure, null, equal to atmospheric pressure, and positive, greater than atmospheric pressure, pressures. Right?
Perfect. Pressure in a fluid point. Through the hypothesis of continuous, we consider an incompressible fluid, that is, with constant specific mass and specific weight, which has a free surface and is subject to atmospheric pressure, as we considered the effective scale, in which the atmospheric pressure is null. By the continuum hypothesis, the fluid point has an elementary area, dA, and is at a depth h. As the fluid point is at rest, we can say that it is subjected to pressure P in all directions. Another point to be noted is that over the fluid point there is an elementary volume dV that can be calculated by the product of the depth h with the elementary area dA of the point. This volume dV, on the other hand, has a weight dg, which can be determined by the product of the fluid specific weight, gamma, by the volume dV, or by the product of the gamma by the depth h and the elemental area dA. Dividing both members by the elementary area dA, we conclude that the pressure P on the effective scale of the point is equal to the product of the fluid specific weight, gamma, and the depth of the point, h. Simon Stephen, 1548–1620. To understand his theorem, we consider a continuous fluid, incompressible, at rest, and that has a known specific weight, gamma. As we know that the pressure at a fluid point, belonging to a continuous, incompressible and at rest fluid is equal to the product of the fluid specific weight, gamma, by the depth of the point, h, we can calculate the pressures at points 1 and 2, which are respectively pressure at point 1 equals gamma times h1 and pressure at point 2 equals gamma times h2. We also know that the pressure at point 2 is greater than the pressure at point 1, because of the fact that point 2 has a greater depth. We can then determine the pressure difference between points 2 and 1 that will be equal to the product of the fluid specific weight, gamma, by the height difference between the 2 points, that is, h2 h1. Statement of Stephen's theorem. The difference in pressure between two fluid points, belonging to a continuous, incompressible and resting fluid is equal to the product of its specific weight by the difference in heights between the points. Pressure load and piezometers. We define the pressure load as the relationship between the static pressure in the section, P, and the specific weight of the fluid considered, gamma. In this application, we consider piezometers, graduated glass tubes that allow the reading of pressure load. In section 1, we observe a pressure load of 20 meters and in section 2, 17 meters. It is important to note that the pressure load unit is a unit of length, in the case of the international system, meter, but it is also common to be given in meter of water column, MCA. So 1 meter is equal to 1 meter of water column, 1 meter equals 1 MCA.
The piezometer works on the effective scale.
Barometer and the absolute scale. To remember the concept of absolute scale, we evoke the barometer, which is the device used to read atmospheric pressure, therefore, a device that works on the absolute scale. The animation featuring a barometer represents the same at sea level. We have mercury, a graduated measuring cylinder and a reservoir open to the atmosphere. We completely fill the beaker with mercury and this allows us to state that there is no air in the beaker. Then we put mercury in the reservoir and it has a free surface, that is, it is subject to atmospheric pressure. Then we capsize the beaker in the reservoir and observe that the mercury drops to the 76 centimeters level and there it remains in equilibrium. Important. We use mercury because it has a large specific mass. It is average. We could consider it equal to 13,600 kilograms per cubic meter. For this description, at sea level we consider atmospheric pressure equal to 76 centimeters of mercury. Generalizing the barometer reading, we would have atmospheric pressure equal to the specific gravity of mercury times the height read from the graduated tube.
I understood, because, in the effective scale, the atmospheric pressure would be equal to 0.
Comparative diagram between pressure scales. We draw a horizontal line that characterizes the absolute vacuum, that is, the absolute zero, which is the zero of the absolute scale. It is important to know that there is nothing below the absolute vacuum. So on this scale we only have pressures greater than or equal to 0. Through a barometer we read the atmospheric pressure, which can also be called barometric pressure. Returning to the diagram, we plot atmospheric pressure from absolute zero. We draw another horizontal line, where all its points represent atmospheric pressure. For this reason it represents the zero of the absolute scale. In it we can have positive pressures, greater than barometric pressure, null pressures, equal to barometric pressure, and negative pressures, less than barometric pressure, but greater than or equal to absolute vacuum. These negative pressures can also be called technical depressions or vacuums. Let us now consider a point A and it represents its effective pressure and its absolute pressure. Note that the absolute pressure is the effective pressure plus the barometric pressure. Important. Barometric pressure depends on temperature and location. In studies of pumping installations, we also need to remember the metallic gauges and the differential U-shaped gauges. Borden-type metallic manometer. U-shaped differential manometer and manometric equation. The pressure read on a manometer is called the gauge pressure, which is synonymous with pressure on the effective scale. The gauge pressure is equal to the internal pressure, entering the manometer, minus the external pressure, which is normally the atmospheric pressure, which in the effective scale is null. The Borden metallic manometer can be found only with a positive scale and there it receives the name of a manometer. Only with a negative scale, in this case called a vacuum gauge, and with the positive and negative scales being called a manovacuometer. To read the U-shaped differential manometers, we use the manometric equation. The manometric equation is always applied to two fluid points. To obtain the manometric equation, one of the 2 points must be adopted as a reference. Starting from this point, marking the pressure acting on it and adding the products of specific weights with the descending columns to it, plus summation gamma times descending heights, subtracting the products of specific weights with the columns ascending, summation gamma times ascending heights, and equals the pressure acting on the point not chosen as a reference. Adopting point 1 as a reference and applying the manometric equation to the sketch represented by the figure, it results. Pascal's law, 1620. The pressure around a continuous fluid point, incompressible and at rest, is equal in all directions, and when a pressure is applied to one of its points, this will be transmitted integrally to all the other points.
Hydraulic fluid is not subject to breakage such as mechanical parts.
Application example: hydraulic brakes. Synthesizing what we study in Class 2. See the animation of mind mapping. Boost your intelligence by solving problems. 11. The device shown in the figure below measures the pressure differential between points A and B of a pipe through which water flows. Based on the data presented in the figure, we ask: 1. Determine the pressure differential between points A and B, in Pascal. 2. Calculate the absolute pressure inside the air layer, with the Borden manometer reading P manometric equals 10 to the 4th Pascal, and the local atmospheric pressure P atmospheric equals 10 to the 5th Pascal. 12. A differential manometer is installed between two conduits through which the same fluid flows, with a specific mass of 800 kg per cubic meter, as shown in the figure below. The pressure in tube 2 is constant and equal to 114 kilopascals. When, in a first situation, P1 equals 1900 m of mercury, The level of the manometric fluid in the left column coincides with the zero of the scale. Determine the height of the manometric fluid, in the right column, in relation to the zero of the scale, when the pressure in 1 increases to 2,280 mm of mercury. Specific gravity of mercury equals 136,000 Newton per cubic meter. The link is at the top right. 13. The installation, shown on the right, has a 1.5 CV centrifugal pump and is located in a place with a barometric pressure equal to 698 mm of mercury. In this case, will it work? Justify. This exercise corresponds to exercise 2.1 of the basic bibliography, that is, from the book by Professor Frank O. Brunetti. In the system in the figure, disregarding the unevenness between the cylinders, determine the weight G, which can be supported by piston V. Disregard friction. Data. Remember to learn and expand your intelligence. Study a little a day. Watch the solution on YouTube and subscribe to the channel Alama Mekflu Resolve. Link again at the top right. 15. A cubic reservoir of 42,875 liters open to the atmosphere has 3/5 of its capacity filled by a liquid with a relative specific mass equal to 0.82. It is necessary to determine the pressure acting on its bottom in the effective and absolute scales. Data. Barometric reading equal to 695 mm of mercury and relative specific gravity of mercury equal to 13.6. 16. A compressor generates a pressure that can be read in the Borden-type metallic manometer 1. When it registers a pressure P1 in mmCA, we have it acting on two U-shaped fluid column manometers, one with dyed water as the fluid manometric and the other with glycerin where we have the heights HA and Hg, respectively. For operation 2, pressure is applied in a closed container that contains water at a height H0 and is connected at the bottom to a hose in which two piezometers have been installed, one inclined and the other vertical, where we record respectively L and HP. Ask. A. The specific mass and specific gravity of water and glycerin. B. The angle of inclination of the tube for operation 2. Knowing that the system at the side is at rest, it is necessary to determine the height h of the manometric fluid that has a specific weight equal to 26,265 N per cubic meter. It is known that the pressure at point A is 45,640 N per square meter and the absolute pressure at point B is equal to 118,840 Pascal. Data. Local atmospheric pressure equal to 95,200 Pascal. Specific weight of water equal to 9,800 N per cubic meter and specific weight of oil equal to 8,036 N per cubic meter. The solutions for exercises 15 and 17 can be seen on my YouTube channel Alama Mekflu. Link on top right. 18. Find pressure in section 1 of the system below. The data for this exercise was collected on the laboratory bench and can be downloaded from my YouTube channel Alama Mekflu Resolve at Complementation of information. Let's solve this problem.
19. To suspend a 1500 kg car, a hydraulic lifter is used, which is shown on the side. The cylinders are equipped with pistons, which can move inside them. The larger piston has a cylinder with an area of A2 equals 5.0 x 10 cubed cm squared, and the smaller one has an area of A1 equals 0.010 m squared. What force should be applied to the smallest piston to balance the car? 20. To reduce the pressure loads read by the piezometers in the figure on the side, it was decided to inject compressed air on them. You are asked to determine the pressure in section 1 and pressure in section 2, as well as the difference in level H of the mercury. Watch the solutions for exercises 19 and 20 on YouTube on my YouTube channel Alama Mekflu Resolve at. Student must not expect to win the fish, but must learn to catch it. The engineer must know how to interact between doing and thinking. In addition, you must be able to solve problems and create opportunities in a sustainable way, and this only happens if, in addition to loving the profession, you have the qualities of persistence, dedication and discipline in always learning. Only advance in the course, after solving the 10 proposed problems. Remember, obtaining your solutions is gymnastics for your brain in order to increase your intelligence. Time passes and I still have death as a companion and life as a lover.